This is example 10.7 from Discovering Design with Chemistry. And the first question asks, a mixture of gases is made with 567 torr of oxygen gas, 913 torr of argon gas, and 131 torr of fluorine gas. What is the mole fraction of each gas? So in the last problem in the book, we learned that a mole fraction is the number of moles of that thing we care about, like just the oxygen or just the argon or just the fluorine, divided by the total moles of everything. I'm sorry, I wrote that wrong. Let me clean that up. The partial pressure is the moles of that thing, whatever A is, divided by the total moles of the gas or the mixture. But we also learned that it works with pressures too. So if we have, instead of saying X of A is the moles of one thing over the moles of the total, we can say just the pressure of that one thing over the pressure of the total. So in this case, they've given us torr is just a unit of pressure, and so they've given us torr, and they just want to know the mole fraction. So we can do the same thing that we did in the last one. We can find what our P total is by adding the pressures, just like we did when we added the moles. So we have 567 torr plus 913 torr, no, plus 131 torr. I'm just going to write torr under or at the end for all of them. And these are all to the ones place, so we're just going to add them just like you would any other integers. All right, so 567 plus 913 plus 131. All right, so our total pressure for this gas is 1,611 torr. And so then we just use that for each of the gases. So X of, was our first one, oxygen. So X of oxygen is 567 divided by that total 1611. And because these are both in torr, that will cancel out. And what we'll be left with is the fraction or the partial pressure of that gas. 567 divided by 1611. All right, so we can keep 3 significant digits, so that would be 0.352. All right, next we have argon. So for that one, our partial pressure is 913 torr divided by the total. So my one's got a little close there. So 913 divided by 1611. Again, we're going to keep 3 significant figures, and so that's going to be 0.567. I'm going to go down below to do fluorine because we've run out of room. All right, so for fluorine we have 131 divided by 1611. Those are both in torr. And so our units cancel just like they have before. And we're going to keep 3 significant figures. So that'll be 0.081. Actually, just kidding, I need one more figure because that first 0 doesn't count. 3. 0.0813. All right, so, and if you added those 3 up, they should add up to 1, so you can check that. I'm not going to check it so that we can move on to the next problem. So these 3, right here, and right here, and right here, those are our mole fractions for each of the 3 gases. And we did those the same way as the last one, but instead of working with moles, we're working with pressure. Okay, this problem is a little bit trickier. It says 50 grams of chlorine gas are mixed with 50 grams of fluorine gas. The mixture exerts a total pressure of 3.56 atm. So we have a total pressure. So when we're doing our thing, our partial pressure for each gas, and we have the P of A or the moles of A, this total pressure is what we can put on the bottom. That's our total pressure. So P total. And then it asks, what is the partial pressure of each gas? In the first half of this example and in the last example, we were given either the number of moles of each part of the mixture, or we were given the pressure. This time we're given grams, and so we have to do some of those grams because this partial pressure equation that we have, this formula, does not include grams. So can we change grams into moles or in pressure? What can we do with it? If you said grams to moles, you're right. So for chlorine gas, I should have gotten out my periodic table so I don't have to flip. So for chlorine gas, the conversion rate is 1 mole is equal to 70.90 grams. And then for chlorine gas, we have, I should have labeled that. This is for chlorine. All right, and then for fluorine, 1 mole is equal to 38.00 grams. And we've been doing those a while, so I won't go with how we got those, but we're going to use those as we work towards this. So we can convert this grams of chlorine gas to moles of chlorine gas, and then we can work from there. That still won't jump us straight to the end because we were given a total pressure, not a total number of moles, but we can figure out the total number of moles because we'll have the moles of chlorine and the moles of fluorine, and we can put those together to find the total moles. All right, so let's start with this one. So we have 50 grams, and we're going to multiply that by the number of grams in a mole of chlorine gas. So 1 mole, 70.90 grams. Our grams will cancel, and we're going to keep 3 significant figures with this. So 50 divided by 70.90. So 0.705. And that is the number of moles we have of our chlorine gas. All right, so now let's do the second one. So for our fluorine gas, let's make that a little bit, yes, I know how to use it. Let's make that a little bit prettier. All right, we're going to do the same thing. We're going to convert from from grams of fluorine to moles of fluorine. So we're going to put grams on the bottom so it'll cancel, and moles on the top. So 1 mole is 38.00 grams. And again, we will cancel out the units that cancel, and we will divide. So 50 divided by 38. And we're going to keep 3 significant units, so 1.32. So that's how many moles we have of our fluorine gas. Okay, why am I putting I'm sorry, ignore me. I get to writing fast, and then I just start changing things. I'm not sure why I put a L in all of those F's when we haven't done that at all. Okay, so we have the number of moles of chlorine gas, and we have the number of moles of fluorine gas now that we've converted them from grams to moles. So to do our our mole fraction, which is not what it's asking for partial pressure. So what the question actually wants is this. It wants the number for each of the gases. It's asking what is the partial pressure of each gas. So it wants 2 different pressures. So what we're wanting is the P of our chlorine and P of our fluorine. My CL kind of doesn't look like a CL, does it? CL. This is what the question's asking for these two things. But we can use our mole fraction we have to work towards that. Okay, so let's go back over here. So we have color. All right, so we're going to find the mole fraction for our chlorine. So if we have X chlorine, that's going to be the number of moles of chlorine divided by the number of total moles. To do that, we need to find the total number of moles because we don't have anything to put on the bottom yet. Because we're going to add, and the 1.32 ends in the hundredths place, our answer when we add those is going to have to end in the hundredths place to keep up with our significant figures rule. All right, so our total is 2.03. So that's our total moles. So 2. And then for our fluorine, I'm going to go ahead and set both of them up, and then we'll do the division. We're going to do the same thing. We're going to take the moles of fluorine over the total moles, and we'll have our mole fraction. So 2.03 is still the bottom because that's still our total, but this time it's 1.32. All right, since I have the blue up, we're going to do that one first. All right, so our mole fraction for the first one is 1.32 divided by 2.03. We get to keep 3 significant figures, so 0.650. And that's our mole fraction. That's not the partial pressure of fluorine, it's just the mole fraction for fluorine. So we'll come back to moving on to the next step in just a second. Whenever you're working problems, you have to keep checking the question and thinking, is this what I'm going for? Is this the answer? If it's not, how do I get to that answer? All right, so for this one, we're also keeping 3 significant figures, so it's 0.347. All right, so we now have our mole fractions for each of these, but what we don't have is the partial pressure. And the partial pressure is related to the mole fraction. We know that this X of A could be moles of the thing over the total moles, but it can also be the pressure of the thing over the total pressure. Sorry for my quick handwriting. You should have these formulas in your book, and I'll make it neat when I write it over here. Okay, so what we have is we have essentially our X of A figured out. That's what this is, and that's what this is. These two are our X of A. So for fluorine, let me get back the right color. So for chlorine, our X of chlorine is 0.347. And that's the same as the pressure of chlorine over the total pressure. And we were given that the total pressure was 3.56 atm. And for this particular thing, we can work in any units because it's not specific. It's just like a fraction or a ratio. And so it doesn't matter if it's in atm or the other problems in torrs, both are fine. So 3.56 atm. And then we also have that the mole fraction for fluorine is 0.650, which means that the pressure of fluorine divided by 3.56 atm, the total pressure, is equal to 6.650. We can use that to find the partial pressures. What we want is that P with the little CL and the P with the F, and so we can just rearrange these. So let's move over to the side so we have a little bit more room to work. So we're going to bring this one up here. We're going to work on chlorine first. So for chlorine, we have 0.347 equals the pressure of chlorine divided by 3.56 atm. And if we multiply both sides by 3.56 atm, we can solve for the pressure of chlorine. I'm going to go ahead and write the P of Cl on this side just to make it obvious that the answer's after it. I don't know, I just think it looks better that way. All right, so 3.56 times 0.347. Now, both of our numbers had 3 significant figures, so we can keep 3 significant figures, so 1.24. 1.24. And the only unit we have in this problem is atm, so that's what we're going to put in. That's what this would have been in also. All right, and then we can do the same thing with fluorine. So the pressure, oops, let's not jump ahead. the X of fluorine, the mole fraction, is 0.650, and we know that that equals the pressure of fluorine divided by the total pressure of the gas. Let's get rid of this. And we can multiply both sides by 3.56 atm. That cancels out, and that's going to leave us with the partial pressure of fluorine. And again, this time we have 3 significant figures with both of our numbers, and so our final answer is going to have 3 significant figures. So 2.31 atm. Now, because this one was a little bit less straightforward than the first one, let's review what we did. The problem told us that we had 50 grams of one gas and 50 grams of another gas. It told us the total pressure of that mixture, and then it wanted to know the partial pressure. The partial pressure of a gas divided by the total pressure of the gas is the mole fraction. So we used our mole fraction, which is this, to figure out that partial pressure. But to do that, first we had to find the mole fraction for each of the gases, which meant we had to take the grams they gave us and convert it to moles, and then use those moles of each of the two gases and the total moles of them added together to find the mole fraction for each. Once we found the mole fraction, we were able to put it in the part of the mole fraction formula where it fits. We already had the total pressure, which went on the bottom of the other side of that formula, leaving us with just one variable to solve. And so we were able to come over here to the side using our mole fraction number and the total pressure and solve for the partial pressure. So it was kind of a 3-step process, converting grams to moles, finding the mole fraction, and then using the mole fraction to find partial pressure. When you're not sure what to do, just start labeling things. Label what you have, label what you need, and start writing equations or formulas that include those things until you figure out which ones are the right ones to take or to use.